It'd be nice if the world was just made up of standard shapes, rectangles, triangles, and stuff like this. But like we found with centroids, what's going to happen is our shapes, our structural shapes, are going to be made up of maybe a combination of certain things. All right? So we need to find the moment of inertia not just of a rectangle. That'd be nice. That's easy to do. We have the formula for that. But we're going to have composite shapes. And before we get to finding moment of inertia for composite shapes, there's one important item that's called the parallel axis theorem that I'll just introduce to you right now, and you'll see how this plays into your ability to find the moment of inertia of a composite shape. The parallel axis theorem says, well, if all I know is formulas for the moment of inertia about a centroidal axis, what happens when I need to find, the moment of inertia about some other parallel axis? For instance, hey, I just got done, finding the moment of inertia about that axis, right? But what happens when I don't want it about that axis? I want it about this axis. What do I do then? Well, the parallel axis theorem says all you have to do is to find the moment of inertia about the new axis is to take the moment of inertia about the axis that you know, like the centroidal axis, and add to it a term a times d squared, where a is just the area of that shape, okay, and d is the distance between the axis that you knew how to calculate, which would be the centroid, the distance between that axis and your new axis. Okay? So, that's the parallel axis theorem, and that's going to become really important as we try to find moments of inertia for composite areas. Okay? So that's going to be real important for us. As far as the process for finding moment of inertia for composite areas, it's going to be similar to what we did with centroids. You remember with centroids, the first thing we did was we broke it up into shapes that we knew how to deal with, right? And then we had a little table, and we filled out that table. The table for us that we're going to fill out when we're doing problems will look like this. Shape, again, because you're breaking it down into different shapes. I'm going to have a column called IXC, which is the moment of inertia. If I say X, that means the moment of inertia about the x-axis. C means the centroidal x-axis, which is the centroidal the centroid is all you have formulas for in your book. Okay? So those are the formulas on page 218. If this was IYC, it would mean moment of inertia about the centroidal y-axis. We're going to have another one called A, another column marked A, that's area. Another column called D. D is the distance we just got done talking about. We're going to have a column called AD squared, which again was that term that came out of the parallel axis theorem. And then I'm going to have an IX total or IY total column. And what I'm going to do here is basically this. All this table is doing is giving me that parallel axis theorem, because I'm going to take whatever is in this column, I'm going to add it to whatever's in this column, and that's going to give me your final column. So the parallel axis theorem was what? IX, about the axis that you knew, in this case the centroidal axis, plus AD squared is equal to your moment of inertia about your new axis. So, I mean, that's really the process. What we're going to do is take all of our shapes, come up with an IX total for each of those shapes, and then we're going to total this up. So if I have 4 shapes, I'm going to have 4 values here. I total it up. There's my moment of inertia. Okay? So like I said, like centroids, this is a pretty, pretty straightforward process. Okay? Questions?